Okay, now we are live,
Uh,
getting live as well. Let's just see.
yeah, we're still not alive, just like preparing the live stream. Or if we, yeah, it's now we are live on Facebook and YouTube.
All right, should I begin there, then, Omer?
Yeah.
Today we will have a very great webinar with our past chair, IEEE Region 8 Young Professionals past chair, Dr. Vinko Lesic. And he is an assistant professor at University of Zagreb, and he has a very great research experience in ATH Zurich and formerly again Zagreb. And today he will explain a great topic on smart precision and predictive agriculture. And I want to give the words to Vinko to explain more about himself and talk a bit short about himself. Vinko, could you introduce yourself a bit more? Of course, all the Region 8 knows you as because you are the Region 8 YP past chair, but there may be still some new guys, and it may be better to learn some more about you.
Thank you, Omer. All right, let's start with the IEEE thing, definitely. So it's really a pleasure to be part of this program. We kicked it off more than 1 year ago. We have a year and a half during this COVID situation. And I'm not sure if you're still counting the numbers. Which lecture is that? Do you have this information, perhaps, Omer? I'm really curious.
Yeah, in fact, last year when you were the past chair, you kick off this Connecting Expert program. So today, the inventor of this Connecting Expert program will be our guest, and I think it will be it is a good feeling. It should be a good feeling with you, and we are also excited about that. And yeah, in fact, you can continue about. And we have, as I remember, that is we have already done more than 60 Connecting Expert webinars. So it is very great for this webinar to be watched so much and organized so long, I think.
Yeah. On one side, we are very happy with. On the other side, we have a lack of in-person events. So this is a thing we can do. But still, it has a very nice touch, and we brought many interesting people here today. And finally, yeah, it came to my turn. You know, I started this program together with the guys. We did it 44 in 1 year, and now we are. Yeah, I think we are closer to 70 already. So, Omer, thank you for pushing it forward after my part in that. Okay, and besides you, I also thank Ali, who is here behind the scenes. So guys, thank you for keeping it alive. And it's, as I mentioned, it's a pleasure to be here, but not right at this point, I'm here on the behalf of this technical talk. So apart from IEEE, where I served as a chair of young professionals in Region 8 last 2 years, and now currently I'm the past chair there. I'm also vice chair of IEEE Croatia section. So if anybody is from this section, hi guys, thank you for watching. And on the professional side, I'm an assistant professor at the Faculty of Electrical Engineering and Computing in Zagreb, Croatia. We are in the Department of Control and Engineering, Control and Computer Engineering. Okay, so that's the official name. Part of the Laboratory of Renewable Energy Systems. So it's a really nice background how we came to this topic. Why do we observe agriculture, in fact? So renewable energy really means that we are, we are observing a lot of climate things, and we have been doing that for 20 years so far. So that's how how much laboratory evolved. And since the first times of wind energy and photovoltaic energy, climate is really our everyday. And also we are using a lot of tools of control engineering, like modeling. Today is very popular to call it artificial intelligence. but we have, of course, deeper ways how to call the methods that we are using, and perhaps some of them I will mention in this presentation. And finally, one step by step, coming from climate, from renewable sources, from these tools, we are now trying to enter this area of agriculture. And we usually do model predictive control for many things. And we started to think, okay, can we do something about predictive agriculture? Can we try to model things in the agriculture? And is there a way that we can influence some phenomena that occur there as well? Okay, so without further introduction, this presentation will be about a little bit about state of the art, so from the technical approach to agriculture, about our projects that we have. I really keep it short just in case you are interested in what's going on, and also to advertise my colleagues because much of this work is also from their part. Then I'm gonna go deeper into what we are really talking about, something that we call encapsulated design, which are really microclimate chambers, and you will see what we do with them. So the thing what we do with them is we try to create big data. The motivation is, okay, I will tell you a little bit more about that later. All right, so drawing from big data, we are going towards models, towards learnings and potential. What can we do in the future with the agriculture? And one of also very tangible already results, there is a micro-location weather forecasting, or today, how they call it, nowcasting. It's really a new term, so I will get you a little bit about that. All right. So regarding of the state of the art today is what we call digital agriculture. So we have a lot of sophisticated sensors and expert knowledge. You know, we usually go into the field and we take these measurements, we take the samples, and we analyze them, and it's what is in the domain of the agriculture experts of the Faculty of Agriculture and institutes and also the companies, large one. That's what they do. It is still today the best what you can get for the insight of the real status of your fields. But the problem is you can do it only occasionally, and it's really expensive to go there. I mean, when you put expert knowledge, that means very expensive again, right? So what we did, we attached a lot of sensors to the drones, and we are flying above the fields. We are using multispectral cameras. We are trying to conclude something. As you can see here on the photo, there is uneven distribution of the colors, and we conclude things from these various spectra, various intensities of lights and so on. And this is finally going towards what we call today precision agriculture. Okay, so in parallel with this, we have satellites in the other orbits, and we are using them to observe the fields itself. So one on the European part is called Copernicus. It's a cluster of satellites system and portal. It's free of charge. You can get it, you can download it, you can examine it. If you're an ICT company, you are required to apply, of course, but really it's pretty much very open and abundant of data. It's really a research domain, so everything you can do, you can also share with the community. It's really becoming more and more interesting, I would say. So at the same time, we started to do this. We applied for this project before there was such a big fuss about climate changes. But now it seems like there is really a strong effort into continuing this trend. So we will see what's the future is bringing. But definitely it's going toward this way. Let's use satellites, let's use drones, let's try to save our agriculture, to put it that way. All right, so this satellite imaging is promising deeper applications to agriculture, definitely, but however, it's still in infancy. As I mentioned, scientific research domain. Although you can get a lot of talks about different companies that they are having a profound use of these images, still it's a domain of, let's say, research projects. Okay, together with industry, but this is definitely not on the commercial level as it is. You can get it in a commercial way that you hire experts and they transfer you the knowledge, but it's not real time, like you're gonna get some trends and so on. All right, so there is another thing I already mentioned, it's called precision agriculture. So what we can do instead of flying the drones and going in person at the fields, we can install a large number of sensors as a mesh grid of all the crazy things that we measure from the field, like humidity and chemical soil content like pH value. And it's really related to the state of the soil and the state of the climate that's happening above the field. Still, there is not much that you can measure on the plants itself, but we are going there. And that part is what you can see example of the photo here. We are starting to put sensors really on the plants. So this one is in particular ultrasonic probe for measuring the plant water absorption. But you have very similar for other applications, so that's it. And then when you have large number of sensors and devices, you are calling it the Internet of Things, you are networking it together, you are bringing all the information to one place, the cloud, you are starting to, put together some trends, you start to observe them. And these are some of the Croatian examples. The presentation itself is intended for Croatian people, so that's how I'm going to mention it a little bit more about our country, but definitely it's a global trend, not only here at our place. All right, so high progress currently is in this deep sensor of how to measure the plant's conditions, and this is also very active area in research domain, but you also have some of the commercial solutions available. Okay, so next stage is what we call predictive agriculture. So we are starting slowly to accumulate all this data that we have gathered. We are slowly starting to make a huge databases of data. Right now, these databases, as I'm going to mention it, they're having lots and lots of input measurements, but not that much of the output measurements, which is also very important if you're going to put together correlation between inputs and outputs. So definitely the outputs can be cameras, as I mentioned, and these sensors that the last thing I was saying, so you are putting probes on the plants finally to get this output thing. So this is also one of the examples. One of the interesting people we try to collaborate with is Vivent company as a startup, as a promising one from Switzerland. Very popular one is Yara for Norway. We also have some at our faculty that are being researched. In fact, I'm going to talk you a little bit more about this furthermore. So what's the idea? They are using some kind of phenomenon, physical one, and then you are having electrical impulses. So for example, here you can see from this photo that this part is a little bit different than from the left and the right. This is part when the plant does not have water. So there is a water depletion stress, and you can really measure it as an electrical signal. That's really finally important, so you can get your condition of the plant. All right, so what we are very home in here as well, especially in our control domain, we are using fusion of measurements. So that means let's exploit all the information we can get, like sensors, images, satellite images, expert knowledge, and let's put it all together. Let's weight it, which one is more important, which one is more relevant, and so on. And then finally, we are concluding something out of it. So that means really comprehensive digital data. And at this point, it's still perhaps the individual person, like what I read from this paper and data you got to me, and then I'm going to advise you how to run your fields and so on, of course, if you're a big, large company. And this is today most of, well, it's not H2020 anymore, it's Horizon Europe project. So this is a European framework for, let's say, funding the research. Okay, and you have a very large number of advertised commercial solutions, but as I mentioned, it's really still at infancy. But infancy today means very ready tomorrow, in 2 or 3 years. And it's really rapidly getting attention because of the COVID, because of the logistics having troubles delivering the food from one part of the world to the other. So local agriculture is definitely what we learned to appreciate during the last 2 years. Okay, and what I'm in fact gonna talk to you about for the remaining of this presentation is artificial intelligence in agriculture. So it's a big trend today, definitely, and many people are talking about it. And you can hear it, in fact, every day, at least 10 times you get the AI. And you don't really get it in agriculture, you get it in other domains. So it's already been proven how to utilize it, for example, for social media or whatever kind of optimization and prediction you need. But in agriculture is a problem because of the lack of big data. So it has not yet passed through the digitalization stage. That's why you don't have data. But the other thing is it's never going to be like the other domains because the measurements accumulation is getting really slow. So if you want to get, like outputs of your plant, let's say corn or wheat, that means you need to spend 1 year for this plant to be, put the seeds in the ground, for it to become a very large plant, to get a yield, to make the harvest, and then conclude this was a very good year. So let's say you need a lot of years to make it happen. You can do it at many fields at the same time, but definitely each field is going to give you different data. So there is no really a repetition there, as you would expect. Let's say everything happens on Monday, everything is happening at the first minute of 1 hour, like in other domains. For example, people travel to work on Monday very eagerly, and there is a traffic jam early in the morning. So this is a repetitive pattern. Repetitive pattern in agriculture means let's do it January every year. And let's hope that this year has similar climate as the last year. So this is definitely the aggravating factor. All right, but there is, like an economist observation always come to establish the grounding, to assess what's really the possibility here. So right now they're saying all this kind of precision agriculture is gonna give us 20% more increase in yield. So this is really, nice number, and it could really change how we perceive the agriculture in the world today. So as I also mentioned, we have climate changes definitely are impacting the agriculture. So if we don't have better understanding how it impacts the plants, then we would be able to mitigate this risk. And definitely eco-production and resource efficiency is very important now, especially in Europe. We are giving a great deal to this part. Okay, so I'm going to tell you a little bit of the overview of the projects that we do here in our faculty, and something that is called Innovation Center Nikola Tesla. It's a spin-off of our faculty for the commercialization of scientific research. So we have a Professor Bilas who is doing a Maslinet project. That means lots of observation of the olives in Croatia, about the pests, about the watering. Olives are always put in the ground. There is a lack of water. It's really the plant itself has adapted to this kind of environment. So every drop of water is really precious for them. And sophisticated sensors and electronics to go there. And this was a few years ago. It's really, I would say, in front of the age of this kind of IoT things. They were developing sensors on their own. We didn't call it smart agriculture back then, or precision agriculture. We would just call it, sensors. Okay, another project, Professor Bilas, is called Sensitica. This one is especially aiming at very, very bad soil. So that means karst landscape. What is a karst? It's kind of eroded stone that does not preserve water too much or any other kind of minerals. So everything is just being washed out when the rain comes. So this is very important to see what is the condition of your plants. In this case, I think it was wine or a vineyard, a very, very nice and expensive wine. Okay, so another professor in the same group of the sensors, Laboratory for Intelligent Sensor Systems, they are trying to make more and more sensors with less and less size to put in the plants, and many different things. Okay, I'm going to switch a little bit faster pace right now to get everything from my presentation. So we have another Professor Matko. He's from my department. They are also doing control, but from the robotics perspective. So they are as he likes to say, out of all the scientific research projects, perhaps they are the most scientific and furthest from the real applications. But it's only his humble way to say it. I don't think that's too far away from the real things happening in the real world. So they are having like a sophisticated, comprehensive approach of many robots doing many things. So robot arm, aerial vehicles, and also some other specially designed ground vehicles, manipulators, whatever. And they are developing the tactile sensors, so you can pick, let's say, fruits from the plants. You are having the observation things, and so on and so on. A lot of this is depending definitely on images and how you observe them, and how you do it in a really fast way in the real-time application. So another part is project is Watch Plant, coming from Professor Bogdan. In general, they are having a lot of these very interesting ideas. In this case, another sensors, but also to conclude some of the perhaps more emphasis on the data analysis than on the sensor development itself. Okay, another project from his, this one is coordination and support action. So that means let's disseminate what our research in the everyday community. And one of the great examples for that is called Drone Days, where you have a really lot of people coming together with aerial vehicles and giving you their conclusions about many things, but also agriculture, definitely one among the other. There is also Professor Žarko coming from the IoT lab. They are doing the back end and also a little bit of the front ends of the IoT system, how to network all the measurements, all the sensors together, how to do it in a scalable way so that you can withstand few million and so on. All right, so enough of us in the PR. Well, it's not just PR, so you can see what's really going on. And they are, I suppose, following the global trend and what's really happening in the whole world, not just at our university. So right now, I'm going to focus more on my project. It's called Smart and Predictive Agriculture for Resilience to Climate Change. We have a logo coming from the IEEE team, so thank you, Hatem, for making it publicly now. So the project is about using these kind of devices. As you remember the words, it's called encapsulated design, which are really climate chambers. These ones are being produced by our spin-off company called Urban Oasis. They are former students of ours who did this as a competition project, then finally formed their startups, and you can buy these products for your home application. You can grow food inside, you can grow beautiful plants, whatever you would like to do inside. And I will tell you more about it, what it looks like. But the important part is that we took this idea from them, bought a few of those, and then made it into something that we call like rapid plant model identification thing for the wheat as a culture that is very strategic for Croatia and Europe. But let's hope that everything that we learn on the wheat we can also transfer it to other plants as well. So this is in fact a big data generator. So I'm going to show it to you what are the contents. So we have, it's encapsulated, so that means it's isolated from the environment. That means that you can achieve microclimate inside, which is different than the outside one. You can play with it, you can permute it, you can increase it by 1 degree of Celsius, you can decrease it, you can increase humidity, create a wind, you can water the plants in a different way, whatever. And the interesting part is that we are having all these things that are listed here. Okay, let me go through that. Let me stick to the presentation. So air temperature, airflow, humidity, soil humidity, pH value, and something, well, lighting in short, but lighting in an agriculture way, observed through photosynthetic photon flux density. And on the other side, we are observing leaf area index. So that is the size of the leaves. So that means the photosynthetic capability as well, but not only because of the area of the leaf, but also of the condition that plant is currently in. If it's having a nice conditions, then it produces lots of photosynthesis. And if it's stressed, then not at all, and so on. So growth rate, also very time development of the plant is very important. And finally, we are relying a lot on the spectral image light intensity of the various bands. So, for example, near infrared, we observe water content with them. Red edge, we observe disease conditions, and the green band, we observe photosynthesis level, for example. But also, photosynthesis is related to the other bands like 850 nanometers and so on. So getting back to microclimate chambers, so what's interesting for with them is that all different corners of this cabinet are really different microclimate zones. So that means you can individually or in semi-individually control what's happening in this corner compared to what's happening in this corner. So that means at the same time, you can impose really different environmental conditions to the soil. And at the same time, you can really simulate many different fields, in fact, so what's happening. Of course, there is some restriction because obviously this is not a field. So our soil volume is smaller and things, but still we hope that we're gonna make very significant conclusions out of it. And this is what I'm going to talk you further on. All right, so we have 8, on this photo, there are 8 plants where there are 8 plant groups. Each group is having like 4 different plants or perhaps even more in some cases. And we have a stage where we can have 3 layers, not only 2. So for the smaller size of plants, we can put together more of them inside a cabinet. So we have 4 devices, so that means really, if you multiply it, you can get almost, well, 36 to 48 planes altogether at the same time. And in 4 microclimate zones times 4 devices, you can get 16 microclimate zones at the same time. If you wish, you can really get up to 48 microclimate zones if you want to water this plant differently compared to this one. But in the agriculture, it's also very important that you have this, how to say, replicability of your plant's conditions. So each plant is a little bit different than their counterparts. So it's really important that you have more than one that you observe. So right now it's on the edge. It's perhaps even a little bit controversial if you are talking with agricultural experts. They would say you need like at least 1 square meter of plants, then you can conclude something and so on. But less than 4, I think 4 individual plants, we never read any paper that's observing less than 4. All right, so a little bit about the cabinet as well, a whole bunch of electronics in this drawer. This is where this probably most of the community listening to this presentation comes from. And we also have water tank, and it's all being squeezed in a very nice way so that you don't see anything of at all. So everything is really in this drawer. There are some tubes coming through the tower. The tower itself can rotate, so you can take out from the door some of the plants and so on. You can also shift it toward the camera and then take a photo and so on and so on. So what's really important from our part is that we are keeping water in this tank at some level, otherwise it's going to die out in a few weeks. And then there is a question, obviously. This is one air inside the cabinet. So how can you get different temperature in this cabinet inside? Like on one corner and on the other corner, it's all coupled together. And is there really a possibility to get different temperatures? So the photo here, as the experimental results, shows you that you really can. And we are doing it by the airflow coming from the bottom part towards the top part of the cabinet. Let me see. Omer, can you please confirm it? Can you see my pointer of the mouse for the presentation?
Yeah, I can see your slide.
And the cursor of the mouse, can you see it as well?
Yeah, I can see your cursor.
Okay, thank you, Omer. All right, so I'm happy to hear because there were a few slides of me pointing things with the cursor already. Okay, so the airflow from the bottom part is going through the heater, and it's getting cabinet stuffed with a hot air, and the top fans are getting this air outside of the cabinet. So if you want to lower temperature. And then also, again, you have a south side, which is facing the sun. You have intensity of the LED lights themselves. So they're also impacting the temperature and all these kind of things. You can get even 7 degrees of difference in temperature between one zone to the other zone. And you have it here. Humidity is obviously something that you can also do it in the same way, relating greatly on these airflows. Soil moisture is a little bit straightforward because we have separate valves from the soils, and photosynthetic light, that means LED lights, that can also be individually controlled. All right, so I will describe, I mean, all of these things, all of these microclimate variables are very interesting on their own and their impact to the plants. I'm going to only talk a little bit about the LED lights. So this is a photo from a figure from Wikipedia when you Google what is the color of the sun. So that really means what is the spectral emission of the sunlight. And you can see here that it really greatly depends on the weather, on the time of the day, and of all kind of conditions. But mostly, for example, if you have blue sky, you have this area, and it's focusing between 400 and 500 nanometers, let's say, and then but also going forward and forward. So this is not a complete axis of the wavelength. These ones are going further towards infrared and so on and so on. Okay, when you come to the LED light, this is what you get from the data sheet of your LED light product. If you remember, so coming, let's say, from 300 and 75, let's say, toward 800, LED lights is having a narrower band, definitely. And the efficiency of this is targeting different stages of plant growth. There is, if you remember the movies, there is a pink light always related to the growing of plants. So the pink light is really good as a mixture of red and blue if you're having your plant at early stage of their growth. And when it's getting a little bit mature, you would love to add a little bit of the green spectrum in it. And there is a whole bunch of science what is the best way and how to do it. The thing is, the common thing, let's say general thing is, we are having this PAR spectrum, which is called photosynthetically active radiation. So everything outside of this is not really something that your plant can perceive. Well, they can perceive a little bit of far red radiation, but then it's mostly influencing your temperature and not the photosynthetic capability of the plant. Well, this is all very general and broad. We could spend days talking about this part, and perhaps if there is a discussion, we can do it here even in the presentation. So another part of the sunlight is intensity. So how much intensity of, strength of the sun or the LED lighting you need to make your plant grow. So this photo is in fact actually this photo from this source from 2008. And then you can see growth rate observed in a very numerous number of experiments in the same conditions. That's how you do agricultural investigation. You have 1 year of experiments or 3 years of experiments, as you remember back from the initial slide. Okay, and so the growth rate goes together with the intensity. And as you can see, near 500, you are starting to get something meaningful. So that 500 means 500 micromoles per meter squared per second, which is ppfd, or photosynthetic photon flux density. Okay, and then when you go to the 1000, then you really start burning your plant. Then it will be very efficient if you put CO2. That's also very interesting conclusion. But also you would like to water your plants here. All right, so if you would like to have LED lights from this to this part, let's say this is a relevant part, you would need like 750 watts of LED light for the right end of the band per meter squared. And let's say it's less than 1 meter distance for that, because light intensity is dropping exponentially with the further you are from the source. So let's say this is 200, this is 750. So if you would like to get this cabinet having the intensity of the sun so you can burn your plants, then you would really need something like this. This is what we are used to see as solarium beds. and their power is reaching even above 10 kilowatts. But let's say the normal one, if you would like to get a nice suntan in 15 minutes, it has to be 7.5 kilowatts of a little bit different light. It's called cold, I forgot, fluorescent light. It's less efficient. It also focuses on ultraviolet, but very similar thing is also for the LED lights for your plant growth. And then you have all kinds of different lights. So let's say LED, COB LED, the most efficient one we have is 2 times watt. Then it's very roughly transferred to PPFD measure. All right. So another part is, as I mentioned, leaf area index. We are now getting towards output things that we monitor. So you can measure it as a millimeter paper. You can go with a tool inside your field. You can put it to the leaf. You can get scan your size of the leaf, and so on. You can do it with lasers, with photography. You can estimate the data. You can really get the complete biomass of your field, but you can also get a little bit more deeper analysis of what is the leaf area index, for example. So that really means surface of your leaf. And then you have camera approach, which is really robotic vision. How you can, you take several shots from different angles, and then you conclude, okay, this is the surface of your leaf, and you can do it real time almost. Well, real time, like 15 minutes or whatever. And then what our research group does, Professor Orsak, I already mentioned him, they are using this approach, but then they are making a blender model of the plant. This is really wheat. And then in this blender model, they can do whatever they wish to do. They can rotate it a little bit and then take a photo. They can rotate it a little bit further, take a photo from all the various different angles, because now this is a 3D model and not a real plant anymore. So they call this synthetic data set. And with that, they compared this blender approach together with convolutional neural networks with some kind of commercial thing, and they got very similar surfaces, less than 10% difference, in fact, with all this data, I would say. All right, so this is an example. We are also, as I mentioned, using lots of various spectra for all these kind of things, analyze it, and then finally we are really creating big data in the end. So how we do it, what I mentioned there, so if you have, let's say 48 plants inside your box, that means if you really want to squeeze it, let's say 2 harvests per year, because you don't need to wait for the summer conditions anymore, because you can put it in your cabinet. Perhaps if you can squeeze really 2 harvests per year, like they did it in Egypt, like the old Egyptians managed to do it with the Nile, very fruitful ground. So it is really possible. We are not yet there, our team, but we hope it's possible. So in other words, you can almost reach 100 harvests per year in all these 4 devices. So that is a really significant difference in what you can observe from the real field. This is very, of course, hypothetical. So we are taking it, with a little bit of distance. Okay, let's see what we're gonna get. Then we're gonna make a conclusion. But so far, this is the idea. And how this idea came to us is this slide here that I'm showing. It's a black box modeling approach. We use it commonly in many different things. You don't know what's your black box. You have some inputs and you are measuring some outputs. The problem is when you don't know what are your inputs and what are your outputs. But we know at least that our black boxes are wheat, the plant itself. The inputs are obviously climate and soil, and the outputs are biochemistry ones. And but this is the only, how to say, general approach. For example, as I also like to say, if you're playing Mozart music towards plant, perhaps it will develop differently than you're just changing climate conditions. Who knows that? But we are concerning only with climate and soil conditions in this case, and biochemistry measurements. So a little bit about the wheat itself. We observe here winter wheat, which is very common for Europe and also our parts from Europe. So that means it grows somewhere in October and the harvest is somewhere in July or August, depending on the year. And in the meantime, the plant develops from stage 0 to stage 100. And this is called BBCH scale. So every, let's say, few numbers of this scale is called phenotype of a plant. So for example, this is like germination, and at this point, it's really not my area anymore. And also I know it better in my local language. But at some point, there are few stems coming from the same plant, and the number of stems, the ratio between the top ones and the lower ones, divisions, they can really make the difference of your plant, how resilient it is to wind, to strong wind, how strong can it withstand the grains at the top. If they are too heavy, will it fall down, and so on. So this is also part of the genetics. But even when genetics occur, it's really greatly depending on the, let's say, soil and climate conditions. So for example, common thing that we have problems with, somewhere in March, you have put too much of the fertilizer, and in the 3 months, you are getting the too rapidly grown wheat, and then it bends over, for example. It can happen. Yeah, it happens every year for some reason. So these kind of things we are trying to observe through this approach. And okay, so enough of the BBCA scale. This part is the winter period when snow has fallen on the wheat. You can see at this point that the wheat is already grown a little bit. So it goes into this hibernation stage until the snow is over, then it starts to grow, mature, and then the harvest finally is where you earn money. All right, so what we know from our plant that we have 100 BBCH numbers. And let's say, okay, let's not observe all 100 of those, it's too complicated. Let's observe only 3 phases of the development. So we observe germination, plant formation, and maturation as second stage, and the final stage as grain maturation. And the inputs we observe are those that I mentioned you for the cabinet talk, temperature, humidity, lighting, nutrients, and those are mostly those. A little bit more than that, but yeah, these are the most relevant one. And then the outputs we are measuring: leaf area index change, millimeter square per day, spectral intensity of various spectra, and also CO2 in ppms. So this is what we can get, and we can get that with cheap sensors. You can also get this from expensive sensors, and the expensive sensor here, that means, let's say, $70,000-$80,000 if you're gonna get precise biochemical measurements of something. We are using like $20 sensor tops, and the expensive one are the spectral cameras. And so more data, big data compared to the quality data and smart data. It's always, you know, like a balance, but here we opted for this case. All right, so we have temperature from some kind of span from 4 degrees to 40 degrees Celsius, and we permute the temperature through this span of values. We also do it for humidity from 0 to 100%. We do it for the ppfd from 0 to hopefully 1,750. Right, I forgot to mention, we are not using 11 kilowatts of LED lights. We are using a few 100 watts of LED lights, and for the rest, we are remaining on the external sun. As you can see, the cabinet is transparent, so that means sun from the outside can come and shine on the plants, at least from the ones that are facing the sun. And also the nutrients pH value from 4 to 10, somewhere kind of a decision. And then we also sample it every 15 minutes to 1 hour. And then after, let's say, 1 hour, we permute it a little bit. The temperature is not anymore 5 degrees. It's now 4.5 degrees, while the rest of the things are remaining the same. And we do that for every BBCH plant. And with that, we're gonna have 500 microclimate, 5,000 microclimate permutation scenarios. And at the end of the project, between 2 years, we are hoping to get 6 million data entries and form our big data, and start to do something starting with that. All right, so this is talking a lot about plants here and not that much about technology, because I don't know, it's kind of a thing that we are more interested in, and the technology itself is something that is not, you know, like on the scientific edge, it's out of the box. But still combined in all the pieces combined in a very interesting way that it's working together towards this goal that I'm talking to you about. So this is our software architecture. All of this data is being sampled and it's being immediately archived on the database on the IT cloud. I think Microsoft Azure, right? From this company Urban Oasis that I mentioned, and then we also take it to our own local servers, and we are doing it, as I mentioned, periodically. So this data that we're going to acquire to the remaining years of the project, we're also going to share publicly, so you can see what we did, what we gathered. You can try to make better models than we did. Of course, you're going to be able to do so because we are taking a lot of time on this kind of things. Oh, a little bit about this one. We have a real-time controller for microclimate measurements. We have envisioning another controller for user interface, but also you can get user interface from the cloud. So it's a little bit combination of modern IoT, cloud, whatever comes to your mind, it's really being implemented there. All right, so models, learning, and potential. Once we have a huge data sets that I'm mentioning, we're gonna do the input-output correlation mapping. In other words, we're gonna do neural network prediction. From the historical data, from the data gathered from the cabinets themselves, but then fine-tuned also from the field measurements. So this is when you establish your model on the emulated data set, this part is done offline. And then when you start getting your sensor from the field, then you can fine-tune this model, and then you can get really tailored model for your own field. That is the whole idea of this. So we expect that it's gonna, let's say, give you some 60% of accuracy. This one will give you 70% of accuracy for something. It's not much as some other applications. We don't expect to get to 100% accuracy never, because it's a very complex model. But still, it's higher than trying to figure out the customer behavior. And then you have also lots of things happening just by observing customer behavior in this very low level of accuracy, or your confidence in the accuracy itself. Okay, so this one is important. I would like to emphasize it again. We're gonna make all this publicly available, so you can monitor our work and also our published papers. At some point, it's gonna get very nice and tailored for you, so you can do your research on your own as well. Okay, so what do we do with AI modules or software? We would like to get yield prediction, depending on the stage of development of the microclimate history, of the plant history, plant type, soil history. We would like to get it finally the yield prediction as the final goal of the agriculture, right? But beyond that, we would also like to treat your wheat in an optimal way, so you can really calculate, once you have model, how the fertilizer will behave in the weather, in the plant itself, how it will get the plant's growth and so on. And the same thing for the pest treatment. This is also another part that you can also, well, in fact, we are aiming to put some of the pests inside these cabinets as well, and to observe how much they are eating the plants, what is the rate of that, how is the leaf losing its green part, and so on. And finally, how the plant dies out because of being eaten or being killed by the microclimate condition, and so on. Okay, but also perhaps not at this point, but somewhere in the future, this is going to be very interesting watering scheduling. Right now, we are just relying on rain, but perhaps that's going to change. It's still changing for some cultures and definitely some geographical locations, but this is a basis to optimize it. So right now, for example, in Croatia, we are having 10 times treatments per year. If you are very smart about it, you do it 7 times. If you reduce it to 5 times, it's going to be a really significant improvement in this part. All right, so also one important part is the grain moisture prediction, and finally wheat behavior in hypothetical climate. So that is, let's see how the climate change will influence the wheat. Okay, so over the time, we are talking a lot with the experts from the agriculture domain, we are going to the fields, we are picking the wheat, we are observing what's happening. And really, at somewhere at this BBCH scale of 20 to 30, which is the plant of this size, you can see compared to the hand, it's a very tiny stage. If you unwrap it, you can take out this small kernel out of it already. And if you put it to the microscope, you can see already the number of the grains containing in this undeveloped kernel. And here you can already count this number, and you can see, okay, this is the most that my plant can reach this year, because all the previous things that took towards this stage of the plant, they are now shaped your plant, and it can only grow toward this number, to this size of the kernel. And it's different for every year. It gets higher and lower compared to the quality of the climate and many other things. We did understand, we took for granted, over the time we build up tradition. We always know that in Croatia, we're gonna put the seed in the soil at the end of October. But nowadays, in the last few years, we really don't have these answers anymore, because the weather is getting really crazy about it. So this is the whole idea. Once again, this is what you can, these kind of things can get your data smarter. So once we know this thing, now we say, okay, we are observing more experiments in this stage than on the other stages. We are also emulating more dense combination of permuted microclimate conditions for this stage of development and for this kind of microclimate conditions. So this is spring. That means you're not going to get 40 degrees of Celsius temperature during this period. Perhaps you will in some of the future scenarios. I really hope not. But that means that you will get temperatures of, let's say, 16 to 20 degrees tops at this stage of the year, and so on. Okay, so all of this we are doing continuously. We are talking a lot of it, from technical experts from the institutes, but also with the home growers, with the people driving tractors every day and trying to figure out on their own what to do, and so on. All right. So a little bit behind the scenes, this is how it's being built. This is how this is the cups that we are putting our soil in. Lots of 3D printing, lots of customization. These are the sensors from different parts of the cabinet, getting the 3D distribution of the heat, of the airflow of the heat, and so on and so on. And this is, you can see MATLAB Simulink, yeah, everything that control guys are doing usually. Okay, so this is one of the recap photo. You can see when you put soil. By the way, a lot is depending on the soil, but we just don't observe all of this together. We said, okay, let's observe most typical European soil with a lot of clay. And this is what we are putting here in our cups. And then once again, 4 zones, over 40 sensors, 8 to 12 simultaneously plants. Okay, this is a little bit selling point. Up to 100 harvests per year in these devices, 5,000 microclimate scenarios, and 6 million data entries for our AI models. All right, and that's about it. I'm gonna very briefly go through this weather forecast correction, because it's one of the most recent things that's happening in this domain, and it's really leaning on the use of artificial intelligence. So weather forecast correction, or how they call it nowcasting, has become really popular. There is not even 1 month ago when the Google scientists did this research for using the DeepMind of the Google AI cloud platform. All right, so what is this in fact? That means that you have weather forecast that's coming from some very complex simulation of the global world climate. It's probably, in Croatia and Europe, it's called Aladdin. This is the software that we are using. And then you have Aladdin 32, Aladdin 16, 8, 4. This number means what kind of size of your mesh grid you are observing as a climate. It is in fact finite element method software. So the 4 as 4 kilometers by 4 kilometers, that depicts the size of your individual element in the finite element method observation. Okay, and then you have it. You have very global, general for this 4 kilometer squared thing. What's going to happen in the next 24 hours, and it's very complex. It takes several hours to do the calculation of this kind of thing, and then when we have outputs here in Croatia, it's already 4 hours delayed. Those are from midnight to 4 a.m. in the morning, so we don't really care about it. But at the 4 a.m. you will get backwards the weather forecast prediction for 1 a.m. So it's really taking a lot of time. The thing is, once you did it, that's where you leave it. This is the forecast for this day, for the next day, for the whole week in advance, and then the next day you refresh it. On the other hand, we are having slowly having a lot of real-time information coming from our climate, from our radars, and this IoT thing, like a mesh grid of sensors and so on. So this is idea how to utilize this current information in the climate and add it together with the forecast to get a very precise short-term forecast. And in other words, we call this weather forecast correction. So how it works, we are using the weather forecast, and we are also using the historical measurements, or perhaps measurements from some distant sensors that we know that the weather will come to our location that we observe now. So in Croatia, this is an example of our meteorological measurements. This is only an example of one producer called Pinova, and these are their meteorological stations all over Croatia. So Croatia, if you don't know, it's a really strange shape. So just connect the dots and you will get the country. A little bit also abroad in nearby countries as well. So this is not all the stations that we have in Croatia. We have many more. We have, I think, perhaps even double than this. Well, not really double, depending who is in charge, who owns the station and so on. But definitely there is a mesh grid of local measurements of weather data. So what is the weather data? It's listed here. Air temperature, moisture, leaf temperature, ground temperature, leaf wetness, precipitation, dew point, and so on. So altogether around 150 meteorological stations throughout Croatia, not only Pinova, others as well. And we started to observe it, let's say 7 months ago. So we have already, well, not anymore 7 months ago, I have to update this one. So 10 months of data, and we are just accumulating it. But the results are based on the 7 months data, so that's also a relevant number here. So for example, we did 2 points where we have local measurements. One is called Sveti Ivan Zelina. It's 25 kilometers from Zagreb, and for Zagreb, you will get your very precise weather forecast. Okay, another point is Vrbovec, which is also I have to check it right. It's also a little bit distanced from the nearest weather prediction point. I think it's Ivanić Grad, never mind. But the important part is that it's a little bit less than 10 kilometers away. Well, this one is 25 kilometers away from what you would expect as a weather forecast. Okay, and these are the historical measurements from these devices. You can plot it, you can see it. You can see when the battery is dying, you can see when it's uncalibrated as well, perhaps. But most of the time, it's very reliable measurements with the precision of the grading of the equipment itself. On the other hand, we are using Open Weather service as a weather forecast prediction. And the Open Weather itself has already a lot of information gathered. It's a really web portal where you can get your weather for the next period of time, 36 hours in advance. You can pay to have it real time, refreshed every 1 hour, or take back into the history. You can do a lot of things here. Still, not all the things, but a lot of things and very important insights in this macro climate and weather forecast itself. Okay, so as I mentioned, a whole bunch of things is already included there. They are also doing some data processing on their own of different sources, and they are really building like their own very nice, interesting weather portal, to say it this way. All right, so if you read this here, different data sources and so on and so on. So when you put it together with the local measurements, so and you use this LGBM light gradient boost method as one of the library methods from Python, TensorFlow, whatever. If you just mix the two together, you will get from the forecasted air temperature in this case, which is the orange line, and the recorded temperature is the blue line. So let's say blue line is what really happened at our location, and the orange one is what we forecasted that's going to happen to on the location. And then when you put correction of it with this LGBM method, you get a green line as getting closer towards the blue one. But still, the blue one is unknown. It's the real measurement, while on the other hand, we are talking about the prediction for the forecast as well, where you don't still have the real measurements. So what we have here is orange is what you would get from your forecast portal. Blue is what you would get in reality, drawn when the time has passed, so you can really draw it. And the green one is what we said with this correction that is going to happen on the location. And even visually, you can see that there is a difference, that there is an improvement here, definitely. So this is for the air temperature. This is for the air moisture correction. This one is doing even better than the air temperature. And also the time plot and so on. All right, I have this tendency to go much deeper into it, but let's just keep it as an overview. And this one was for the Verbovets. If you remember, that one was closer. This one is for Ivan Zelina, that one was further. And there is also like a very general tendency that the further ones get higher upgrades, while the closer one has a little bit less upgrades and correction. So in terms of number, you got mean average error from open weather of 1.89. You got a mean average percentage error of 9.46%. So this is the error, right? So it's 10% missing what we have really on our location. And then when you put correction, it's almost half of it, the reduction of percentage error, and also perhaps on the mean average error. And this is the temperature for Svet Ivan Zelina. We have temperature for Verbovets. You can see this one has a much larger error. It's also a bit corrected, but still not accurate as, for example, Svet Ivan Zelina. That means Verbovets is having trouble with the mountains around it. Well, not mountains in Croatia, but let's say hills and so on. So weather is unpredictable, changing in this location. Then also humidity. And then finally, you get like 30 to 60% better, whatever you do. And this is really the where the world is going to be imminently happening into agriculture. So all this, we will also try to add on our models for the cabinets, as I mentioned, for the wheat models. We will try to see also from how it's going to behave on different fields, not only in the cabinet itself, but really on the real life locations. So this is it. I talked to you a lot about the agriculture. Thank you for being here with me. Perhaps it's a little bit more overview of presentation than being in the depth, but I think it's really important because we are matching at least two of the scientific areas together in an interdisciplinary way. And we are not only having technical guys here behind this research, there is also a faculty of agriculture with lots of their knowledge. And there is also lots of talks with the people on the ground to really see what's behaving and how is it behaving, how is it similar, how is it general, and so on. So once again, thank you for listening to me. And right now, Omer, I'm getting back to you on the topic, how usually you go with these presentations.
Thank you very much, Rinko, for this great webinar. And first, I'm looking for the question by the attendees. And this is really an interesting topic because, there are many words on when people say agriculture, they consider the biological issues, some other concept. But if you want to make a smart agriculture, and we should consider some other AI techniques and some other technologies to get more efficiency, so to make the agriculture efficiently. And this is very important, especially in these years, because in this year in many Mediterranean countries faced some forest fires and some other issues. So the resources become less and less, and in this case we need to use our lands, our resources, agriculture resources better to meet our people's need about that. And I just want to say, you are also on the you are also, as I remember, lead of the Region 8 entrepreneurship initiative, right? So what do you think about that? For example, I participate in I participate in entrepreneurship, social entrepreneurship contests by MIT Seoul. They determine some topics, and for example, I participate in Resilient Ecosystem Challenge. And what do you think about that? For example, you give very good examples, and do you think to organize such a contests based on climate change or cultural issues, or these issues, I say, with similar topic, do you have such a plan? I just wonder, after watching this webinar, after following this webinar, I think it may be very interesting to make such a entrepreneurship contest on climate change issues. What do you think?
Yes, thank you, Omer. So right now, there is what you mentioned, there is something called IEEE Region 8 Entrepreneurship Initiative, and it's bringing this combination of technology and business together, because we are technical people, but we are not only technical people. And there is a lot of business based on the technology, so that is really all right. Let's try to support it from the IEEE side. That was the idea. So right now we have 3 programs within this initiative, and one that is currently happening is called Entrepreneurship Week. So this is a series of events in IEEE sections, which are really countries in the world, and where you have local ambassadors who are organizing events of this part of this program. And the events are free-form, getting lots of people talking about the technology, about the trends, but also a little bit of education, what you would like to get, how to raise funds, how to get things, how to prepare your presentation, and so on, how to protect your intellectual property, whatever. But one mandatory thing of this event is the competition for the startups. We call it elevator pitch competition, so that really means the best presentation, but the presentation itself is reflecting the startup who is representing it. So we're taking all of these events in all of the countries. They are having this kind of competitions. They can be more than one event per country, and that's it. So the local events will select top 3 competitors, and they will hand it to us back to the region, and then we will make a huge pool of the best startups from all over the region. So let's say about 50 startups, and then we're gonna take it to the next stage. We're gonna make this international competition of all of them and select the best few. So 3 best or 4 best are selected by the committee of IEEE Region 8 experts, and the remaining 2 are also given the chance to get it through the social media and the number of hits, like an audience popular choices. And the common topic of all these events is called sustainable engineering. So climate changes and resource efficiency all comes to this sustainable engineering, very wide topic. So we are really interested in making our world more efficient and more sustainable place, to preserve it, to protect it, and from IEEE part to do it by technology. So you are invited to look out for your local events If you wish, you can contact us. This is my business email, but still you can send me an email and I will just point you to your local event as well.
Thank you very much for your answer. I just wonder that, and thank you very much for promoting also these events. Thus, the audience can follow the Regionate entrepreneurship initiative. And this is my only this was my only question. I say, yeah, not the other okay, techniques. Ali, do you have any question? Or maybe he don't have any question. Okay.
I don't have. Thank you for participating.
Thank you, Ali, for inviting me.
Thank you very much again for your participation, dear audience, dear participants. And it seems today we come to the end of our session. And it was really our pleasure to host our past chair, Winko, and to benefit from his experience. And I think we still have much to learn from him as an academician, as an entrepreneur, and as a very good guy, very good friend. And thank you very much, Winko, for your valuable time and giving this great webinar on this vision, explaining your vision.
Thank you, Mary, also for your time. I remember it's never easy to organize such things, especially in the crazy world. You really devoted a lot of your personal time for that, for the whole program. And thanks, one big thanks for you guys, for both of you here, and for the team that's behind the scene and not currently now with the switched on cameras. Okay.
It is our pleasure to continue this great webinar series created by you and Almedin, and thank you very much again. It seems we are at the end.
Okay, so goodbye to the public. I suppose we can remain here for a few more minutes, or
goodbye.